Just a little clarification for the homework. Use pload equals 450. That's what's loaded in the MATLAB program, and use in MATLAB program and the Lagrange method. And we're borrowing the generator costs and the load from problem 3.7, but that's it. So in the book, 3.7 has A, B, C. I think it has D. You're not doing those. We're just pulling the generator costs out of that problem, and we're going to do 450. Okay. There was a question that was something that I hadn't made clear. So that's the homework that's due. That's due Friday. So today, somebody says they can't hear anything. Boy, I tell you. I wish I knew how to make this thing run better. View. You know, it says here that my microphone is talking to you. So it says I'm talking to you. Testing. I can see well, it doesn't have a meter. It has a bunch of pixels that jump up and down. Okay, now why am I not setting anything up? I don't know. If you can't hear me, people, I dislike WebEx intensely, and now you know why. Now you know why I intensely dislike WebEx connector. Let's see if this has got something to do with it. I'm going to mute the speakers now. Please send me a text if you're okay, if you're receiving me now, okay? Somebody just sent a little message. Somebody just sent me a message a minute ago here. I'm going to assume either that or you can send me a text message on my phone so that we know that we're in business, please. Let's see. It's okay now. Zinji Liu, thank you very much. Okay, so we're in business with the audio, and I'm going to make sure that that my phone is off. That's primarily so that I don't get a phone call from somebody on the outside that's looking for me. So today we're gonna talk about unit commitment. And it just means generator on or off. Generally on a large power system, you do not want all the generators to be on all the time, because there would be too much generation during low load hours, such as nighttime, weekends. And so you need to put more units on when the load goes up. So if we have, and you had an example of this in the book, but if we have a load that goes up and down, and here's 12 hours, and then it comes back the next day, and let's say it goes up and down again, 12 hours. Then we put a unit on, let's say this much, and it covers that much generation. Sometimes we'll put a couple units on, and they call that base load. And that just simply means that this is one generator, this is megawatts here, and this is megawatts over here. Some generators run base. That means they just run. Nuclear plants are that way. They like to put them on and run them, period. They don't take them down until they're ready to change the fuel. And then maybe later on we put another unit on here, and then we keep adding units on. You can see what's happening. I'm having to put enough generation on, and maybe I run some more at the top here to cover in case I have a loss. So these are all units. I keep adding them on. So I'm turning on during the morning rise, and then in the evening turn off. Okay? And I have to do that. Now, generally, we have to worry about meeting the load and any commitments that that a particular area would have if it's going to export power. If it's importing power, well, then it can take its load and say, well, some of that's being supplied by imports, so I subtract off the imports from the load. That's how much generation I have to have. But then we have to have something, and this is the time to bring this topic up. But it's a crucial topic, and that is the topic of spinning reserve. It says I've got a bunch of generators here, and they're all connected. Okay, so here's the breaker. I'll put the breaker here like this and show you that it's closed, and here it's going off into the power system. And let's say I just have 4 generators, and suddenly I lose one of them. Now, a generator can go offline very quickly. A large generator unit, steam generating unit, can have trouble with its boiler or with its turbine, or with the generator itself, the electrical side of it. Anything in there, and they have to take it offline quickly. And the first thing they do, of course, is open the breaker, let the unit slow down. They vent the steam, if it's a steam unit, out the roof, and so forth. Now, the problem is now that I have a shortage of generation. Where should it come from? Well, in the way this works, let's say that this is the big world out here, and some of my lines go out to other systems over here where they have more generation. I'm going to come down here to a bus, and I'm going to have more generators down here and more generators over here. So the outside, I have a huge interconnection with generation. Now, if you are the island of Puerto Rico, down in the Caribbean islands, they don't. What goes? They go up to the shore, up to the beach in Puerto Rico, and that's it. There are no cables, or there are no connections. Sometimes you will have this. You will have a country that's electrically isolated, doesn't interconnect, but it is always in your advantage to interconnect as much as possible. The larger the system means what happens is I lose this generator, And all these generators start to go up just a little. So this is just showing that the megawatts of each generator starts to go up a little bit. And they all go up a little bit. Maybe some of them don't go up much. Maybe some of them are at their max. So they all go up. They all participate. Everybody comes up. Well, you can't see that with my hand. They all come up. And what does that do for you? Well, it means that part of this loss of generation is made up on my own generators, but much of it is made up coming in over the transmission system from other systems. Now, so there's a reliability issue here. The more generators that I'm interconnected with, the more reliable the system as far as the loss of a generator. That it means that the system will be less and less affected if there are more and more generators out there. Now, however, these other generators have contracts to buy and sell power, and they don't want to be supplying you with power for a couple days while you repair this unit. They want this unit's power to be replaced, and so these units are going to have to go up enough to replace all of that power and make this go back to zero again. Okay, so this is just, I'm just going to put another arrow and say this is back to zero, meaning all of these generators go back down. So they came up for me and they all helped out, and then they go back. But these go up and they increase enough to make that up. Now, you can't do that in a quick enough time by connecting a generator, even if it's no matter what kind it is, you cannot connect it in and bring it up. You could with some hydro units, but right now we're talking about big steam generation. You have to have the unit connected, synchronized, and delivering power. That's what we mean by spinning. It technically would be to say it's spinning, synchronized, and so forth. And it just means that these have the ability to go up. Now this is the important thing, is this arrow in here. Okay, they can all go up. Well, that means you have to, you can't operate these generators at their max. All those three generators can't be at their max, because then if I lose the first one, if I lose this, I don't have any, I can't draw on anymore from these generators. And everybody, the power system is broken up into areas, and each area has to carry enough spinning reserve so that it can increase its generation to make up for the loss of a large generator. And believe me, it happens. You can have a generator carrying 700,000 to 800,000 megawatts, and bang, it goes offline because of some problem. And suddenly we have to act quickly. We have to have that reserve ready to make up for it. Now, initially, the whole interconnection in the U.S. That includes all the generation from the Atlantic Ocean over to roughly the eastern side of the Rocky Mountains, and from the Gulf of Mexico up to and including a lot of middle Canada. Now, there are some exceptions to that. Texas is an exception, as well as parts of Quebec, Labrador, those utilities way out on the eastern extremity of Canada. We'll go into that later on when we talk about generation control, but we have to carry enough reserve, and so the sum of PI on line, meaning spinning, has got to be greater than or equal to P load plus P, let's say we're exporting, plus let me get this. Let me get this. This is, I'm going to put the max in here, plus the reserve, P reserve. So I've got to have at least this much power. Well, I'm going to be generating these amounts, but I've got to add some reserve to this so that I have more. And so if the reserve could be as big as the largest generator on the system. Some areas, they make it the 2 largest generators. So then you have to put more generators online. Okay, so you put generators online to meet the load, meet the export requirements, and to meet that reserve requirement. More on this later when we get into the chapters on automatic generation control. All right, well, the issue is combinatorial. It's a very hard mathematical optimization because if I have 4 generating units, it can be let's say 1 equals on, 0 equals off. So if you just use your counting binary counting, 0 0 0 0, they're all off. And 0 0 0 1, this will be 1 2 3 4, and number 1 is on. Here's number 2 is on, and 1 isn't, and here's 1 and 2 on, and so forth. Okay, so there are 16 combinations. Now, obviously, some of those combinations don't mean a thing. All the units off? Well, what's that? That doesn't mean anything. It's not supplying load and so forth. But we want to know what is the best combination for each hour. Now we'll come back to this later on because it gets very complex. It's a very complex problem, unit commitment. It's another one of these problems that the electric power engineering community, if you will, worked on for many years and went through really as far as I can say 4 different stages of solving this problem. Stage 1 is really just seat of the pants, do it whatever way you can. A typical way of doing it is to simply have what they call a priority list. And it simply says when the load gets to be a certain amount, we add generator so-and-so and keep it on. And then as the load gets higher, when it gets up to the next point on our priority list, we put the next generator on and so forth. And so there's a priority list. The first generators, first or second, are on all the time, and then we add the next one, and then the load goes up, we add the next one. Very simple, no optimization whatsoever. And that was used for years. You can implement it by hand. You can just use a piece of paper and a pencil, and that's what engineers did. All right, stage 2, dynamic programming. The first papers that I know of were written by a friend of mine named Chuck Pang when he was a PhD student at Purdue University. And he wrote, and that became the standard means of solving until, for about 15 years. that was the method of solving, and people worked on it and worked on it and worked on it, and you could get dynamic programming codes. So we're going to go through the dynamic programming solution a little bit today to familiarize you with that. And then stage 3 was called Lagrange relaxation. Remember we talked about a relaxation technique simply means that you look at some problem variables and say, yeah, I know they're variables, but I'm going to just assume that they are constant for the time being and solve my whole problem around that, and then I'll go back and adjust them, and then I'll keep repeating that. We will talk about this one on Thursday, the last stage where we have come in the last 10 years is full. You can sometimes call it 1-0 programming. Some people call it integer programming. There was an independent company. I got the Cplex. I think that's wrong. Ceplex. I'm going to call it Cplex. And Cplex was bought by IBM. And they marketed this 1-0 programming tool, and a lot of the large electric marketplace vendors adopted that. It produced better solutions. It's a very complex. I do not pretend. I have no background to get into 1-0 programming. There are one of my students took a course on the campus once where they did cover part of the techniques that are involved in 1-0 programming. But it turns out that MATLAB now has some capabilities in this area. And one of my students did a project a few years ago where she programmed a unit commitment using 1-0, the MATLAB 1-0 programming tool. I don't know. There may be more competitors out there to the IBM/Cplex tool, but once we show you the formulation of the Lagrange relaxation, well then we've defined the 1-0 programming tool. We're going to cover this one very extensively today, and we'll cover this one on Thursday. And if I can get it set up properly, I will give you a code that we will have you do some exercises with a large Lagrange relaxation code to get an idea of what kind of things to worry that you can do with it. Okay, so dynamic programming. Now I have this is an example that came out of it comes out of our textbook, and we got it from one of the beginning. Whoa. I don't know if I'm going to be able to show this whole thing. I can get it on there just like this. It's a wonderful example to show what dynamic programming is all about, and it comes from one of the basic books on dynamic programming. And when we published the book, our publishers, I don't know if they paid them. And we got permission from the publisher of the book on dynamic programming to use this figure. So here is the idea. I'm going to go from picture these things as cities in the United States. So you know, for argument's sake, we can call that San Francisco, and over here is New York. The rest of the analogy breaks down. I'm not going to try to name any more cities. But the point is that these represent the cost to go. So it costs me two units of either fuel or cash. Let's just say fuel. 2 units of fuel to go from A to C. It costs 5 units to go up here to B, and it costs 3 units to go down here. And what I want is the optimal path, the least cost path across there from A to N, from A for San Francisco to New York. Now, I was looking at this morning and thinking, well, maybe it would be interesting to see how many paths are there. And I thought, yeah, how are you going to do that? I know how to find the minimal cost path, but getting the total number of paths, but it's a large number. It's a very, very large number. If you had a way of enumerating the paths, and you went off and you started to enumerate them, you might be able to enumerate all the possible paths for this problem and then simply check off the lowest cost. You'd say, there, I solved it. Well, the problem is that once you get a little bit larger than this, you'll find out that as we get into the dynamic programming for unit commitment, that the number of paths gets to be enormous. You cannot possibly enumerate them all. You'll be there for years and years just enumerating, and you won't solve the problem. So in this case, we're going to show you how the brilliance of dynamic programming and how it broke down the problem into very simple, what we call staged process. And so I want you again to notice the dotted lines, and we've arranged that all the cities fall on these dotted lines, and we can kind of call this stage 1, 2, 3, 4. Okay, pardon me, 1, 2, 3, 4, 5. There's a reason for that, but it's not strictly that necessary. But for now, we're gonna talk about this as a stage process. Now notice that if I'm going to start from here, what I'm going to do is I'm going to go up to the top here, and I'm going to say, well, if I took this path, then it cost me 5. So here underneath here is the cost. Okay, and the cost to get here is 2, and the cost to get here is 3. So if I'm at one of these points, I know exactly how much it's going to cost to get back. Now we're going to assume that the cost is the same in each direction. That maybe didn't need to be, that should be said. Now suppose so it's 5 units to get there, 2 there, and 3 there. Okay. Now look at point E over here. This is where the dynamic programming comes in. What I want to know is, if I'm at E, should I come this way to get back here, or should I come this way? Should I go up to B and down, or should I go down to C and back? Well, let's talk about the cost. So what I need to know is that this cost is 11, and if I have the 5 there, then 5 plus 11 in here, 11 plus 5 equals 16. So if I take those two paths, it will cost me 16. Here, it would cost me 8 to get from here, and it will, I know that this one is 2. So this will be 8 plus 2 equals 10. And all I do is pick the least, so I put a 10 inside there. So now I know not only is this the cost, but I have an indicator out here, and I could put an asterisk that says if you're at this point, the least cost path is here where the asterisk is. I don't need to put an asterisk here because there's only one path back. But I know that the cost from here, the minimum cost back to A is 10. Here at F, if it's 2 to get to C, and then I have a fuel cost of 4, then this is 4 plus 2 equals 6. This one is 3 plus 6, 6 plus 3, I'll write it, equals 9. Well, then the cheaper cost is this one, and this is the least cost path back. Down here, it's 2 plus 9. 9 plus 2 is 11. Here it is 3 plus 6, or 6 plus 3 equals 9. So this is the least cost path. Now, here's the interesting thing. At this point, when I'm looking at these cities, I have already marked what is the optimal path back to San Francisco. And I know the cost, and I have accumulated it. The cost here, now I'm not picking the minimum yet for the overall, but I want to know if I got to here, what would the cost be? Now notice that when I get to do any evaluation further to the east over here, I don't have to worry about anything back here where I've got my hand. I do not have to worry what path, what's the cost. It's all written down right here. It's all got in that number. That's the minimum cost inside there below the letter. And I've got an asterisk that tells me which path to take to get that minimum cost. And you're going to see that this is, I just keep doing this. So over here at H, here it's 10, so that's 10 plus 3 is 13. This one is 6 and 8. 6 plus 8 is equal to 14. So there's 2 in here. So I know that the cheapest path is this one over here and 13. So I will come back down this way. Here, it's 10 plus 2 is 11. Is 12. Plus 2 is 12. Or it's 6 plus 11 is 17. 11 plus 6 equals 17. So here's the optimal path is over here. And I keep doing this. Now, once again, and down here, I don't have to worry. It's 6 plus 5. There's only one way to get there, so that's this path. And here it's, 6 and 9 is 15. 9 plus 6, 15. 9 and 4 is 13, so it's this path down here. When I look at those cities, I don't have to worry about how I got there. All I need to know is that at this H, there's the optimal path, and the cheapest cost is 13. I don't know. I don't have to care what method or what series of steps I took to get here. Same thing here. I know that's the optimal path and that the total cost is 12. Here the optimal path is 11. Here it's 13. Once in a while you will get the optimal path will be the same, and the answer is you can pick either one. It doesn't matter. So let me just finish this here. 13 and 9, okay, is 22. 12 and 3 is only 15. Coming up here, 11 plus 7 is 18. So I know it's this path down here. And there's my cost, 15. Over here, It's 6 and 12. 6 plus 12 are 18. It's 11 plus 8, 19, or 13 plus 5, 18. Now notice, here's an 18 and here's an 18. So I could pick either one. It could be this one or this one. It doesn't matter. I'll put an asterisk next to both of them. They're both the same cost. And at last, now, I get to the end. 15 plus 4 is 19. 18 plus 3 is 21. 18 plus 3. So the optimal path is here. So all I know, right now I can tell you that the optimal path takes 19 units of fuel. And I start here and I say, there's the optimal path. So I come back to here. And I don't know if you can follow this. I'll make it big, thick. And then it comes back down here, right? So there's the optimal path. And you know, each time I come back, all I need to do is follow the little indicator. And I come back. So I've completely, each stage I have separated the problem out. There is my optimal path. 2, 8 is 10, 12, 13, 14, 15, and 4 is 19. So there's the optimal path. But the important thing is that at each stage, I write down the indicator and the total cost, and then I go to the next stage, and I don't care how I got there. The next stage, I don't care how I got there. It's a very, very powerful principle. It's called the principle of optimality. And dynamic programming has been applied to almost every problem on the face of the earth. I'm serious. Optimal control problems, problems in economics, problems that you name it. Dynamic programming has been applied. I would say, frankly, that linear programming still, to me, I would hold out as the more useful of the two, but okay. Be that as it may, I can find the optimal path by just doing very simple. I didn't have to enumerate all the paths. Well, now, and I will put this in with our notes. We'll call this page, where am I here? It'll be in here like this. It'll be page 3A, in with the notes. So, what we do with generating units, and I'm gonna go through a generating unit problem today. But let's talk about what Chok Pang did in his original thesis work. He basically said, "But look, I'm gonna list all the combinations on the left-hand side, but it's useful to put them in there in some sort of an order." And the best way of thinking about that is to put them in an order of increasing capacity online. So let's take 4 generators again, and I'll number them 1, 2, 3, 4, and here we go. All the units off. The first unit on, the second unit on, the first off, both the first and second on. This is just counting in binary, you know, like a computer would count. Let's see, where am I here? 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, etc. Until we get, how many more states? I gotta go 1. 0, 1, 1, etc. until I get to the top. This is one of these cases where I didn't plan for 16 lines in here. In any event, this says the first unit's on, the other three are off. This one says the second one's on, the first one's off, and the third and fourth are off, and so forth. Notice that I keep adding capacity as I go up. So this is a safe way to do it, unless number 1 is a much larger capacity than 2 or 3, in which case the total capacity won't be going in strict rising order. If this is smaller than this, and this is smaller than this, and so forth, I believe that this will give you an order where the total capacity is going up all the time. Now, so these are the unit statuses here. Unit on, off, status. The word status means whether it's on or whether it's off. Okay, we don't have any indication what the output, what the P for the generator is. We will assume that it's between its min and max, unless it's at 0. See, and unless the status is off, and if it's off, then P equals 0. All right, now here is time. And so here's my first hour, hour 1, hour 2, hour 3, hour 4, and so forth. Most of the time you run unit commitments for 24 hours, or more typically for a week, 168 hours. And what we know is we know what the total load is. And so let's say I'm going to put a dot here that represents if during a certain hour, let's say during the first hour, this were the state. Number 1 was on and these 3 were off. Then that dot says in the first hour, that's the state. Okay, so I've got a series of dots. Now you're going to see the similarity of this to that minimum cost across the cities problem that I just did. Here I've got the same dots, but they're at hour 2. Here, same thing. So I've got dots like this, and I'm slowing down because I have to draw them all. We'll do just a few hours. So, what I want to know, suppose I start the problem off with this state right here. There's the start. That's the start. And in the second hour, I'm going to show you a path. The second hour, I turned on number 1. Then I turned on number 3, so I went all the way up to this state here. And then in the last hour, I turned off number 2, so I came back to this state. Now, notice that this represents a path. So the states, all these dots that represent these on-off states here, represent a path from left to right in this dynamic program solution. It represents a unit commitment. So what we're saying is that we started out with this state, number 2 is on, and then we turned on number 1, and then we went up to where all the first 3 units were on, and then we went down to here where I turned off number 2. For whatever reason, that's a path. And I could calculate the cost. Now here is the hard part about unit commitment, is because sometimes there are what we call path-dependent costs. So what is the cost from start to end? The total cost Well, it's the economic dispatch over all generators online hour 1. And the economic dispatch again says that it's the minimum of the sum of the Fi of Pi plus lambda times the load minus the sum of Pi. We're going to ignore losses, okay? And we've got the generator limits in this. It's an economic dispatch, hour 1. Then economic dispatch, and then when we've calculated this, then we give the value, what we call the production cost at hour 1 is equal to the sum Fi, and let's say Pi. We'll put a star, meaning the optimal, right there. That's the economic dispatch for that hour 1, and then we do it over all generators online hour 2, and it's the same thing again. Minimize the sum of Fi, etc. Plus lambda PL minus the sum of the Pi. Okay, so then I get the production cost hour 2 equals the sum of the Fi of Pi star for hour 2. And so whenever I've decided what the path is, that's the total cost until I get to the end. Now there's more to it than that, and this is where it gets to be interesting. I will say interesting. It gets to be a very painful thing to do this because of these other restrictions. But that's part of it. So we could say mathematically, okay, so it's the sum from t equals 1 to let's say the number of time steps is t, and each time we'll do I equals 1 to n Fi of Pi of t, and this thing says for only online generators. So for each hour we know which generators are on or off, and then we calculate the minimum by economic dispatch, and then we add that up over all the time periods. Well, there's some other costs now, and this is other costs. One of which, hello, this thing is supposed to be. Let's see if I can sufficiently mess it up. There we go. It's supposed to be autofocus. And I think sometimes it just loses its way because I'm waving my hand around underneath it. All right, other costs. What we call a startup cost. Now, if I have this, and I go up to another dot that represents. This is a dot here, 0011. That started up unit 1. Particularly large steam generating units. You don't just go over to the large. It's not like an automobile where you go over, you put your keys in the ignition, you turn it. Actually, today, a modern car, you don't turn the key necessarily. Just go over it. As long as the key's in the pocket, you press a button and the whole thing starts up. But it starts up instantly, or practically instantly. If it's a car of the generation that I drive, I put my key in it and I turn it and I give it a little gas, and it comes to life. Okay. How much gas did I use in starting it up? Very little, and I'm ready to go. Now, however, if I had a car that said, well, you can't do that. If I had a car that said you start it up and you have to run it for 2 hours, then at the end of the 2 hours, you could go. Well, that's wonderful. What does that mean? Well, that means that for 2 hours, so let's say that I had a car and you turned it on, and 2 hours later, so here's hour 1 and hour 2, now I could go. Well, this represents burning of fuel. The car is running at a certain RPM and it's consuming fuel. And it says if you want to go at this hour, 2 hours previous, you got to go turn the car on. There were cars like this. Not in my time, as old as you may think I am. But there were cars in the United States. I suppose there were some in Europe and other places that ran on steam. They had steam engines and probably burned oil. And you went to the car and you started up a boiler, and you had to put fuel into it to get the temperature up and then get the steam pressure up. Original locomotives on railroads were the same way. If you wanted the engine to start moving at noon, maybe you had to go to it and start the fire in the engine's fire compartment with coal, and that took several hours to get it up to pressure and temperature. And then you could start using the locomotive, or you could start using in the U.S. that was called the Stanley steamer. I've seen pictures of, I've seen movies. There are movies where people have them and they've restored them. And the Stanley steamer went down the street, sounding like a small steam engine on a railroad. Anyway, large power plants. Suppose you want to produce power at 4 p.m. Then you have to turn it on maybe at noon. For 4 hours, you're burning fuel just to bring the steam up to pressure, all the pipes up to the right temperature, and start passing steam into the turbine. And near 4 o'clock, you start it turning until you get it turning fast enough, and then you synchronize it and close the breakers, and now you can produce power into the network. But for 4 hours, you consume fuel. So they call that consumption of fuel is the start-up cost. Okay, so that fuel that you used is the startup cost. So now we come back. And you remember my example said that here's hour 1 and hour 2. And I said, okay, I do the production cost at hour 1 as the sum of the Fi of Pi, optimal cost, doing an economic dispatch of all the units that are actually online, and and then from that hour to the next hour, if I'm going to do a combination that includes starting up, well then this one has a startup cost and it has a production cost. Some Fi, Pi, optimal at hour 2 plus the start. So it's the sum production cost hour 1 plus the startup costs plus production cost hour 2, etc. we talk in the book that there are other more complicating factors than just the startup cost. Another complicating factor is the fact that some units come on, and because they're very large steam generating units, they once they're started up, they say, okay, we don't want you to try turning it on after we've taken 4 or 5 hours to bring it up to steam pressure. You're not going to just run it for 1 hour and then turn it off. It doesn't make the whole thing is uneconomical. So you're going to bring it up, and then it's going to stay online for let's say 5 or 6 hours. They call that minimum uptime. There are similar rules for minimum downtime too. You turn the unit off, then you can't turn it on again for a certain period of time. These are the complications. And so what I thought I would do is do an old problem in from the book, and I will put these at the end of our notes today. Well, let's say this is from an old exam almost 10 years ago, 9 years ago, 2008. So we're going to do a sample. Unit commit problem. And we have load that looks like this. The load is at 600. Now, you might look at this and say, Wallenberg, are you crazy? You can't just double the load. Well, I did, because this is a made-up problem. And then it's going to go back to 800. These are megawatts. So this is load, hour 1, hour 2, hour 3. Now let's see. Load, each period is 1 hour long. Okay, so this is 1 hour, 2 hour, 3 hours. There are 2 generating units up here. And I'm going to need to give you more information in these sheets. I got to add another sheet to this when I put it with the notes. The first one has a capacity of 600. There it is, and this one has a capacity of 800. So we will now. Over here, let's superimpose in red the fact that there are the states 0, 0, 0, 1, 1, 0, 1, 1, and you know that the capacity here is 0. Here it's 600. Here it's 800, and here it's 1400 megawatts. Capacity on. Okay, so it's just simply the 600. This is unit number 1, and this is 2, and this is 1 and 2 here. Okay, now I made up a worksheet that looks like this, and I can't get it all on the screen, but you'll get a copy with the notes. But here it is again. I don't know that I necessarily need the worksheet because I've got it on here. So when the load, and we're going to assume that we're starting from down here. That the first thing we're going to do is the units are off. Now there's also startup cost. And the startup costs are 300 for unit number 1 and 1100 to start up unit 2. And those are in dollars. So I'm starting down here at 0. If I just start up the first unit, now we didn't say anything about spinning reserve, and in fact we're not caring about that right now. So I could go from this state up to here. So we'll put a dot here. We'll just draw our dots that correspond to these states. And let's see, and down here and down here. Here's all the possible states of the system. So I have to have some generation, so I could go from here to this dot. And note that I get a startup cost S equals 300. That's because I turned on unit number 1. Suppose I went up this path. Well, then the startup, instead there I started up number 2, so the startup equals 1100. Here the startup equals, both units startup equals 1400. Okay, I could turn all the units on in the very first hour. Now, if I've done that, then what you get in this problem is it says for hour 1, I gave you the production costs. So I said, here's the economic dispatch. If you turn on this generator in hour 1, you're gonna spend $32,000 per hour to supply power at 600 megawatts. So that's this unit running completely all out. If I turn on the second generator, I get a more economic dispatch to run the second generator. If I just run the second alone, if I run all 3, I get a cost like this. Okay, so here's the economic dispatch. So this is the production cost here for hour 1 at 600 megawatts for each of those combinations. Now I gave you that so that in this homework, not homework, this was a problem. So this is the production cost for the hour depending on the amount of load. Now, what happens, I want you to look at this point here. Well, the load is 1200. So I can't, and I just drew a circle here. It says that's not a feasible point. For that matter, neither are these points down here at the bottom. I'm not supplying anything. So here, with a 600 megawatt generator at hour 2, it does not supply the load. And neither does it do it with an 800 megawatt, so that's no good either. So you've got to go all the way up here. So now everybody has to converge on this solution by going up to the top there. Okay. Now, what I want to note is, let's go back and say, well, what was the production cost here? It was 32,000, and with the startup, it was 32,300. Here it was 16,250 divided by 17,350. That's adding all the extra startup cost. Here it was 17,938 with a startup all added of 19,338. Here is the production cost, and here's the path cost, what I'll call the path cost. What is the path cost? It's the production cost plus the startup cost back to the previous best state. Well, in this case, the only choice is the beginning here. So now I've got, and notice that now I've separated the thing. I don't care about anything to that side of it. I don't care what happened to the left. I have encapsulated here. Well, and now I need to know, well, okay, here the production cost is 43,250. Here, 43,250. maybe I get some more startups in here. What is the cost? And you have to say, well, okay, no startup cost. Then it's just this 19,338 added to that. So there's a cost to come over here, which is 19,338 across this way. This one would equal 17,350 plus an S equals 300, because here I started up number one. Okay, this was number two on, number one off. I started it, so now that's gonna add onto that. It's gonna make it 17,650, and this one here is 32,300 plus a startup cost of 1,100, so it's what, 33,400. And you come up here and you then get this plus the minimum of these, which would be what, this one in the middle. So this comes out to be 6,900. I will give you the answer key for this so that you can look at the exact numbers when you see the notes. So from here we could go here, we can go here, or it turns out we can't go here because this isn't enough capacity. And it turns out that the production cost here is 24,437 with a path cost of 35,337. Here is a production cost of 25,250. Wow, that's low. Path cost 86,150. Forget it. There's your best solution is just to go across here. So the best solution is to turn on number two, then turn the first one on, and then keep them back on. So let's see, we got your optimal path, I believe, is this path here, like this. Okay, and that's, we have solved the unit commitment. It said for hour number one, we've got the combination 1, 0. It's this one. For hour number two, it's this combination. Hour number three, it's the same. Now, I'm going to show you some of the techniques that they used, because this this may look easy, but it is not. Here's the difficulty. So is your large utility, and you've got something in the order of 40 generating units. Well, the number of combinations is 2 to the 40th power. That's an enormous number. Enormous number. And even with very, very large, very fast computers, you can't possibly enumerate all the paths. If you think about it, if I have, here's states, okay, 1, 1, 1, 1, 1, and it goes all the way down to 0, 0, 0. So there's 2 to the 40th of them, okay? Whoops, 2 to the 40th. For any one state, I've got to look at the possible paths that I would have to evaluate is what? Is the second hour is again 2 to the 40th. So there's 2 to the 40th paths. And then for the next one, there's 2 to the 40th, okay? So the number of possible path combinations is 2 to the, here we go, Bruce, 2 to the 40th times 2 to the 40th. it gets to be, and you can't, it just, the problem blows up. The dimensionality problem of dynamic programming. They used to call this the curse of dimensionality. It's a huge problem. You can't solve it that way. But never hold back the engineers. Chuck Pang was an engineer. The people that were developing this, I knew them, and what they said was, "Oh, look, we know that the top units aren't going to come on, and the bottom ones all have to run just to meet the load. And so we know that there's only a small range of units around here, so maybe 6 or 8 units that during that hour that I don't know exactly what combination will be on and on what are on and off. These are all on and these are all off. And the next hour, it's maybe a little bit bigger. So I've got ranges in here, and so I don't look at any combinations that go from here to something outside of this group. So I'm only looking at combinations in this red from here to here. And now you can play with the tuning of this. And I know when I worked at Control Data, which is now the division of Siemens out here in Minnetonka, they had Control Data was founded originally in the 1950s as the company building the largest supercomputers in the world, and the company you went to for scientific computers. If you had a lab doing any work in atomic physics or something like that, you used a Control Data computer. A lot of electric companies used Control Data computers, a lot of government utilities. And those computers, so they took and they said, well, let's make this bigger and bigger. And they would have those computers solving unit commitment for hours and hours and hours, evaluating possible paths to see if they could, if the cost would be significantly impacted. And they did a lot of research around that. But Control Data sold those systems for many years. They had the most powerful computers, and they would. One of their selling points was that they had these large computers that could solve large unit commitment problems. So that was one of their selling points. Remember, way back, in the beginning of the course, I talked about save 0.01%. Okay, or well, let's say 0.1%. Is it worth it? Well, when your fuel budget is multi-billion-dollars a year, you do the math. You can buy a lot of computers. You can build a building. You can hire a staff, and they can be at it doing computer studies to save that extra 0.1%. That extra 0.1%. So the answer is yes, it's valuable. Okay. Thank you all. Thank you for. I think we each week I learn a little bit more about how to do this thing. I realize that I have to go. There's a point down here that says connected to audio, and thank you for using the little text message thing that we had up there to talk to me. And I will now, when I'm done here, I will put all these notes together, scan them, and I will put the video file up. We don't know why the video file was put up last week and then immediately disappeared. The IT people and I went through all that and just threw our hands up, but fortunately it seems to be working now. So this will be up online later tonight, and you can, those of you that didn't see it or you want to watch it again, I hope you're taking advantage of the fact that you have the textbook, you have the video lectures. You really need to watch the video lectures before you watch the WebEx presentation, and then you can also go back to the stored videotapes that I have generated. Not videotapes. Listen to me. That's my age. The video files online, and you can watch it again if you wish. You can watch it at 3 a.m. in the morning. Just, if you can't sleep, as I've told people, if you can't sleep, watch my videos. You'll fall asleep. Okay. So any difficulties? And if you want to go on that tour of OSI, please sign up. Eventually, we will have to get a list, make up a list of people that are going to go, and come out to the. It's about an hour drive out of the cities, but I think well worth it for you to come and see. You're welcome to talk to them about their unit commitment program. You can talk to them and say what kind of, you'll be able to get some meaningful questions in. Okay? So let me know if you're interested in that tour. Okay, and I'm going to shut this thing down now. All I do is I go and I go over here and I say leave meeting, end meeting. Bye-bye.